Hello and welcome. My name is Abhishek. Today I'll be demonstrating a distributed micro e-commerce architecture designed to showcase change data capture or CDC. The system operates on Spring Boot microservice backend orchestrated by Netflix Eureka and inter-service communication handled by declarative Feign Clients. Our primary data store is Postgres and with Redis functioning as an aggressive caching layer to reduce the database input-output operations. To achieve real-time cache invalidation and state synchronization without relying on dual writes, I integrated Debezium and Apache Kafka. Debezium tails the Postgres write-ahead log, captures the row-level mutations, and streams them as immutable events to Kafka topics. An isolated inventory synchronizes a microservice, then consumes these events and updates the Redis cache asynchronously. Let's initialize the environment. Okay, I'm spinning up Kafka in Kraft mode and have already deployed the Debezium connector via Docker. For Debezium to capture events, the Postgres configuration file was modified and the val level was set to logical and a dedicated replication rule was provisioned. So let us see the dashboard. So this is the dashboard. Let me connect to the WebSocket. Yeah. So before we simulate the load, note the system strict temporal configurations. Redis product caches the product details with time to live for exactly 300 seconds. Our active user tracker utilizes a concurrent hash map with a 2-second sliding window purged by a scheduled thread every 500 milliseconds to guarantee memory safety. Finally, the backend broadcasts a telemetry to this UI via the WebSocket exactly once per second. Now let's start the simulation. I'm now initiating a multi-threaded simulator. Background threads are acting as concurrent clients, aggressively querying the the get product endpoint at randomized intervals. Notice the active user count is stabilizing and the metrics updating in real time. Under the hood, the product microservice is handling this throughput using a double check locking pattern. When a request arrives, it checks Redis. On a cache miss, it synchronizes the thread, verifies the cache second time to prevent cache stampedes or the thundering herd problem, queries Postgres, fetches the inventory via Feign client, and finally primes the Redis cache. Subsequent read operations are served in constant time, big of 1, directly from Redis. Now let us observe the CDC pipeline in action. I will execute the write operation by placing an order. When the order is placed, the orders microservice commits a transaction to the Postgres, decrementing the inventory. Instantly, Debezium detects this binary change in a logical replication slot. It serializes the before and after state of the row into a JSON payload and publishes it to the Kafka topic. Simultaneously, our inventory synchronizer service equipped with Kafka listener annotation, consumes this message. It passes the updated inventory state and issues a call to the product microservice to execute a set if present operation on the Redis cache. Because we rely on the write ahead log, this pipeline guarantees eventual consistency and zero data loss, completely decoupling our ready heavy cache layer from our transactional database operations. Let me stop the simulation. This event-driven approach extends far beyond simple cache updates. In enterprise architecture, CDC is an industry standard for command query responsibility segregation or CQRS, keeping read-optimized NoSQL SQL databases synchronized with the relation systems. It is also highly utilized for low latency ETL pipelines into the data warehouse, distributed logging, audit logging, triggering serverless workflows based on database state changes, and transition from monolithic to microservice architecture. By leveraging Spring Boot, Debezium, and Kafka, we have transformed a rigid polling based architecture into a highly event driven ecosystem. Thanks for watching.